Okay, so it is week 9, and we were just discussing a few issues with the last quiz, so I thought we'd take a peek at that. Anybody want to volunteer to just let us look at your particular quiz? Do you mind, Rain? Is that too invasive?
Not at all.
Okay. 7 and 8, 21 attempts, not bad. Display options. Not yet graded. Let's just take a look here. So Tim has mainly been grading these as they come in. I'm only going to focus on the wrong ones. Okay. Which type of crude oil is in greatest demand? What's the answer there and why?
Like sweet.
Yeah, and it's just, and the reason, yeah, it's just easier to, it's just less, it's cleaner for one thing, and there's less additional technology that goes in to turn it into the transportation fuels that we've been discussing. Now, could be that somebody else is like, gosh, I love that stuff. I want to get all that sand. I'm going to put that into the foundries. I want all that tar. I'm going to put it back in the roads. So there's a market for everything, but primarily transportation grade fuels is where you're going to get pretty good bang for your buck. Not necessarily all of it. Plastics too. It could be some of these heavier, dutier, longer change molecules or better for turning into plastic. So
So this is my first test.
target changes all the time. That's all
Did it not
right.
register my second test?
I'm sure it did.
Yeah,
I'm sure it
up
did.
there at the top, if you click number 2.
Oh, okay, cool.
You're in there.
I actually got that correct when I took it again. I don't know what happened. I know I selected it. When I scrolled down, I must have accidentally clicked and clicked the wrong one on
That's what
accident.
happened on 2 of mine. When you
Oh.
scroll, sometimes it takes it down that and it doesn't scroll.
Yeah, that one's pretty obvious. Okay.
So I think when I click that, let's go over to the blank space and click and then scroll down.
It's pretty obvious. I'm guessing that tar sands.
That one was a little goofy because it says 9, 1, 16, 1, and 21 in the book. But
Yeah,
you just gotta keep reading to find it.
yeah, let's take a look. What
It actually says that the perfect one is at 14.7.
what figure,
14.7 to 1.
And then if you keep reading, it then tells you the 20.
The 21?
Yeah, it's,
what figure is it? That's worth going over. I know it's in there somewhere. Sounds like you guys found it.
it's gonna be in chapter 8. And
Page 295, 294.
Page 295, page 294. Yeah, so they were looking at the air-fuel ratio.
Yeah, 294.
Well, isn't that for a diesel engine
Well, it doesn't say.
It says air lean burn engine
Well,
is
it says for
21, which is
petrol.
why I
Oh,
went 21
that's
several
for
times.
diesel.
See, I think
Yeah,
that's
over at the
16.
second paragraph in 295, it gives you around 20 to 1. After it gives you the 16 to 1.
though? Because for gas engines, compression ratio and octane number on page 286, it says 7.5 to 1.
It's not compression though, it's the fuel, the air fuel ratio.
Not the same.
No, I struggled with that too.
This test, I had 19 minutes left the first time I took it.
Yeah, that's a tricky one. So if you look at figure 18.3, you can see that the NOx, well, the green line is the NOx, and it's a little bit. Let me just pull that figure up while I'm talking about it. Chapter 8. I'm just looking at it right now, and it is a tiny bit deceptive. I think this is the right figure. Okay, so if I were authoring this figure, I would not have put NOx right in the crotch there between the red line and the green line. In fact, while we're on the topic, if you guys want to get sort of a little more serious about your graphing theory, in fact, just last night, I posted this textbook as a recommended textbook for 291 and 292. It's the visual display of quantitative information. This book is the Bible, if you will, for how to make graphs and charts of sometimes difficult to comprehend numbers. And, a lot of what we do is exactly that. So if you get a chance, take a look at that. Anyway,
What information?
it's called The Visual Display of Quantitative Information by Edward Tufte. So this green line, I would have put NOx like right up here, so you got HC, CO, blah, blah. And what you can see by the time you get out to 20 to 1, the NOx have sort of fallen off. The efficiency, well, fuel consumption, it doesn't really, there's no miles per gallon curve on this thing. It does say fuel consumption, but you could be consuming a lot of fuel, but you could also be going really fast. So, but, from the book, it says, if the mixture is made slightly weak, it's 16 to 1, and right at 16 to 1, we can say there's a peak. So that would discount immediately this answer. Because at 16 to 1, you're actually maximizing the amount of NOx.
Well, the reason I actually selected 16 to 1 was because on the prior page, it said that it actually used the word, this perfect mixture is 14.7 to 1.
Oh.
So I went 16 to 1 because it was the closest to what that they had deemed perfect. Then when I missed that, I just went over to what they had said on the second paragraph of 295, where it said around 21.
Yeah.
That it had no time to actually form.
Where do you see,
The mixture can be weak or still around 20 to 1, then combustion can be made to proceed so rapidly that there's no time for NOx to form. That's why I ultimately went with it.
But honestly, no car is gonna run on 20 to 1.
no, and
There's
it's,
not enough fuel.
Yeah.
Yeah.
It'll detonate so bad, so.
Yeah.
That's,
Very-
it's kind of a bad question.
They're just asking you what would be the best as far as emissions is concerned,
Yes.
not run, actually the engine
Performance.
running.
Exactly.
At the very top of 294, 14.7 parts by weight of air to 1 part of petrol. This is called the stoichiometric ratio. It's perfect mixture.
Yeah, that's why I went with the 16 to 1, because that was the only time I seen the word perfect.
mhm. And just like anything, there's no such thing as perfect. You're always picking your poison. Yeah, you might have a good ratio, but your car's not running. Okay, 25, 32. Yeah, transportation. Industrial, this would be, somebody using lubricants. Back in the day, you used to use oil for heating, but, really anymore, you're not,
And that was another Google.
Yeah.
I Googled it and everything I seen was on industrial. I knew
Oh.
to start with that it was either industrial. or
I just remember
transportation.
that because I think we had talked about it in my sure. That transportation is what it was mainly used, products. And I think that was even from when we started talking.
To be completely honest, I don't look up any of the true false questions. I read the question and take a best guess and move on because I know I'll get it right the next time.
Yeah, I was sitting in a committee a while back. There's the Interstate Renewable Energy Council, and we're still working on getting accreditation there. But they're like, don't use true false because it really does not test the student's knowledge. So we're slowly getting rid of those. Okay, is this something several of you are
Yeah, that
struggling
was the
with?
one
Okay.
where-
I knew it was either gas to oil or gas to coal, but I didn't know which one.
Yes.
Yeah.
Yeah, we can't,
You can't, if you just think about it,
yeah, how would you turn gas in the
Into
coal?
coal.
That's right, it's in the book, but it's not, I just, all the.
I read all the different areas, and,
Yeah.
and I never seen anything about gas to oil or gas to coal, and I knew it had to be one of the two, so there I go again, I knew I had two potential answers, but I didn't put a ton of thought into it, I just answered one, and then when I seen I got it wrong, I.
Yeah.
We're, sorry, and just tell me where you saw that in the book. I don't know off the top of my head. You guys are, it's a little fresher in your heads.
It goes through and explains on quite a few of them.
This was the end of chapter 8, or chapter 7.
I think it's the end of chapter 7.
Yeah, gas to liquids, CTLs, coal to liquids. So it's like 254, 255.
Yep. This says all processed, so yes, 254.
Oh, where we go? Yeah, okay. All right. Methane is a calorific value. Okay, so there's, and I'll just,
What do we find question 35?
what's that? This is where it's been just a little bit of,
Well, 35 was the one that I was like, that, yeah. That was based off of a chart.
I couldn't find. the
Yeah, but
answer.
that number's not based on that chart.
No, where is that book?
Page 248 was the only thing I could actually find on it. And like he said, they gave the answers in visuals, so then I tried doing that.
Well, no, I was talking about the 14 kilograms. The correct answer is 14 kilograms of carbon.
Oh, yeah, that's, I would love to know where that's at, the search and search.
yeah, let's spend a little bit of time on this one. Okay, so the question is, according to your text, how many kilograms per gigajoule by combusting methane? So let's just go back to our story problem, dimensional analysis skills that we've been working on. So we're looking for kilograms per gigajoules of methane. So, and I'm just going to kind of start into this blindly. It says a more concentrated fuel is produced. Methane has a calorific value of 55 megajoules per kilogram. So let's just start with that and see what happens.
That's where I got my 55.
All right. Okay, so we're looking at, and that's energy. I mean, that's the typical way that energy density is expressed in energy per unit mass or energy per unit volume. So let's start with that. Well, in fact, we can do it this way. We could just say 1 kilogram per 55.5 megajoules. All right, so we're going to start here, and we want to end up here. So to do so, I'm going to use my method and write in. So I've got megajoules down here. I know that I need, what do I need? I need gigajoules on the bottom. So I'm going to put 1 gigajoule down here. And I'm going to put 1,000 megajoules up top. Right, so if I just run this guy, well, let's see what.
Where'd you get the 55.5 numbers from?
Oh,
Page 354, right in the middle.
I'm reading on page.
Definition.
I'm reading on page 254.
Okay.
Right after the stoichiometric equations are given. It says a more concentrated fuel has been produced. Methane has a calorific value of 55.5 megajoules per kilogram. I'm guessing something of that nature is also Googleable. So if I take my 1,000, divide it by 55.5 equals 18. Write that down, 18.1. So it's 18.1 kilograms per gigajoule. Those guys cancel, those guys cancel. That's methane. Now we're looking at 14 grams of carbon. Let's see where that comes from. I should go ahead and write that out. It's of CH4. All right, so now let's pop back out to the periodic table. So it's asking for carbon rather than methane. And if you guys ever are, out there reading the scientific literature, they're like, it's important to know what they're talking about. Carbon dioxide, methane, carbon monoxide, et cetera, because there's going to be a hydrogen kicking around there somewhere and oxygen kicking around. So carbon has an atomic mass of 12 and change. Hydrogen has an atomic mass of 1 and change. So now if we write this guy out, so if we've got, there's a couple different ways, to do this, but more or less the, and I'll write it out like so. So the atomic weight equals the number of carbon atoms plus the number, no, maybe I'll write it like this, MC, HC, the number of hydrogen atoms. So in this case, we're just going to do methane. So for methane, we know that equals 1 carbon plus 4 hydrogens. And we know the atomic weight of carbon is 12, so equals 1 times 12 plus 4 times 1 equals 16. And you can go right back and pretty much do that in your head, right? So 12 plus 4, 16, no problem. Now what we need to do is go back to that 18 and figure out what fraction is carbon and what fraction is hydrogen. So in this case, we know that, let's see, what's the best way to do this? More or less, so let's just say hydrogen equals 4/16, carbon equals 12/16 of the total. So pretty simple. Carbon is 1/4 of the total. Carbon is 3/4 of the total. So now if we want to say carbon total equals 12/16, which is the same as 3/4, times the total amount, 18.1. 18.1. Do that little math, so 18 times 3 divided by 4 equals 13.5.
I guess where I'm lost is, when did we learn this?
Well, did Tim not cover much the stoichiometry last week? I mean, it's
the first time I've seen anything resembling this at all.
Oh, okay. Well, I mean, it is in the book on page 254, and it is an important part of the class, so I don't mind spending a little bit of time on it right now. And in fact, probably the best thing to do on this, guys, because, this is, pretty important stuff. I mean, it's obviously not a chemistry course, but let's just take a look. Later in the course, we will get into a little bit of nuclear theory, and we dig into this a little bit deeper. But let's just take a little bit of a look at the carbon atom itself. So if we go back to the orbitals right there, you can see that the carbon atom has 2, 4, 5, 6 electrons total. That means that it also has 6 protons. That's what that little number right there means. The number 12 down here means that it has an atomic mass of 12. So it's got 6 protons and 6 neutrons. That's how heavy it is. The fact that it's got 6 protons is what makes carbon carbon. The fact that nitrogen has 7 protons is what makes nitrogen nitrogen. Hydrogen, you go back to the orbitals, pretty simple. 1 electron, 1 proton. That's what hydrogen is. So let's draw a little picture of that guy. So here's a proton, here's an electron, and that's hydrogen. Carbon, you got 1, 2, 3, 4, 5, 6 P's. 1, 2, 3, 4, 5, 6 N's. That's the nucleus of the carbon atom. Let's draw a little circle around that guy. And then you've got a couple electrons, and I'm going to draw one as up and one as down. That's just kind of the way they come in pairs like that in this little first 1s orbital. And then there's a 2s orbital, there's another up, and there's another down. So there's 4 of them. And then there's another couple that are kind of kicking around in this bigger orbital that's called the 2p, and there's one over here, and you've got another one sitting out over here. And that's your down. So that's kind of the graphical way that an atom looks. It doesn't, because the nucleus is really tiny and the electrons are flying around. But what you can see is this hydrogen guy over here. This one electron can sort of, maybe I'll pick a new color for hydrogen. This new little electron can sort of sit over here with its little proton over there, so you can have a hydrogen sitting over there. There's room for another one right over here, another E minus, another proton, and that's your hydrogen sitting over here. Now, if we go back to the periodic table, as I sort of click through these little boron, carbon, nitrogen, see how those little dumbbells change direction? And just like there are 3 directions in space, X, Y, and Z, that's the easiest way for the electrons to sort of align or distribute themselves around the nucleus. So there's your X, there's your Y, there's your Z. So we go back to my funny little picture. All I've got going right now are X and Y. Let's throw in that last Z. There's sort of nothing really there because carbon doesn't have any extra electrons. But here comes hydrogen saying, hey man, I'm ready. I'll play. There's one of them. And here's the other one. Hydrogen. So now you got one big fat carbon, and 4 little hydrogens. And this is just the way nature likes it, even though nature seems complicated. It likes things simple. Because what methane's trying to do is look like neon. See neon there with all of its orbitals filled? So methane is just a carbon and 4 hydrogens pretending to be neon. That's all it is. And it's stable. It's stable in the atmosphere the same way neon would be. Okay, so to get back to all this stuff I was doing up here, I think you guys understand the units. I mean, we've been doing unit analysis all semester, just converting from kilojoules per megajoule kilograms per megajoule to kilograms per gigajoule. This is probably what you're saying you hadn't seen before. So I know that the methane molecule itself has 1 carbon and 4 hydrogens. That's right there on page 254. And I think in general that's pretty common knowledge that that's the chemical formula for methane, CH4, the simplest hydrocarbon. So if I have 1 carbon right there, which I do, and 4 hydrogens, I can then just say, well, there's my 1 plus my 4, so just taking more or less what I've drawn.
Also, it's a 14-to-4 ratio, which is how they got this. It's 14 to 4, because there's 4 of them, there's 4 hydrogens, and only 1 carbon. Carbon's 14, hydrogen's 1.
Yep.
So that's where it's the 14 to the 4 ratio
Yep.
out of the 18.
Yep.
That's where you get that even 14 number.
Yep.
Okay, that makes
Yep.
sense now.
Yep. Yep. More or less. The way it turned out, I ended up with 13.5.
That's because you went 3/4, but isn't it, it makes sense to me that if you take the atomic number, which is 14, and there's only 1 of those, and then you take the atomic number of hydrogen, which is 1, and there's 4 of those, that's 18.
Atomic number of carbon is 12.
12.
Nitrogen's,
What was that number on top where it was lined up with 14? Right there.
so not,
That's just its placement, to be honest
Just a
with you.
column.
Oh. Oh, well, it just so happens to be in column 14.
Oh.
That's not for me.
oh, okay. No, the 14, that's the atomic mass of nitrogen. Yeah.
And then going vertical is the number of orbitals and electrons in it.
Yeah. So 13.5, I'm a little worried though that my answer doesn't align exactly with what,
I think when you type it on the calculator, I don't know if you mispunched or something.
oh, maybe let's see, 18 divided by 4 equals times 3 equals 13.5. Now, I don't know if I think I made a little error there. Well, just to be safe, let's take 18, I'm sure that's right, 18.1, 18.1 divided by 4 equals, so this is going to be carbon total right here. And then the hydrogen total is going to equal, that 18 is correct, 4.53, let's call it.
No.
Let's just double check. 14.5 plus 13.5 equals 18 and change. So let's go back to the exam. 14, well, if you round up 13.5 to the closest even number.
Whole number.
Yeah. Yeah. So, okay. So that, I apologize if that was not covered sufficiently, if you hadn't seen it, but, this is, sits right at the foundation of chemistry, so it's important that you know this
I
stuff.
was just curious because I read the whole chapter, and I didn't find a single mention of kilograms of anything in an amount. So
Yeah.
I was just curious as to where it actually was.
Yeah, you can blow past it.
Yeah, I didn't even find 55.5. I I mean, I saw that it was talking about methane there, and I.
Well, I found that, but I didn't know what the calorific value, because then it also says the pure carbon is only 32.8 megajoules per kilogram. So I didn't know which one of those to take and use, and yeah, I was confused.
So here's your, there's why you got the answer wrong.
What page was that on?
You use the word from instead of in.
Oh, my Lord.
But I think I've said this, I don't know, this is probably the fourth or fifth time I said it in class. That's just the way Moodle operates.
Yeah, but I believe I actually took it directly out of the book as it stated it.
What's it say?
Right there.
It says the dirtiest fuel.
Heavy oil is the,
I even typed in dirtiest fuel
Oh.
when tar sands came up.
really?
Yeah. Like
Oh,
everyone
I
just-
Googled it and it said tar sands.
Mhm.
So I was like, well, it's gotta be one of these two.
Yeah, 259 heavy oil and extra heavy oil. The world's principal source of this heavy oil is in the Orinoco Basin of Venezuela.
What made me so certain was because they actually say that it's larger than the oil source of Saudi Arabia, which is part of the question. I was like, man, it has to be.
We're,
So I
because
changed
of
my
its very
answer on the
excellent.
second test, and I would like, put me worth credit on that one.
You're fine. Yeah, and it's dirty because of all the sulfur.
Well, and that was the other mention in the tar sands spot. It didn't mention anything about sulfur, and it also mentions the sulfur had to be extracted in this, so
Mm-hmm.
like three of the main points of the question were answered in that.
Yep. All right. Hey, well, I'm glad we had a chance to look at that. It's a good exam. All right, so we'll take a break, and then I can either do Chapter 9 on electricity, or we can talk about Summary 3, or do a little bit of both.